Let us look at proposition number 54. Now, before we actually look at proposition 54, there is a lemma. So let's look at the lemma first. There is as such no statement, so I'll just describe the lemma. We are given two squares, AB and BC, such that AB and BC are placed such that DB and BE are in a straight line. If they are in a straight line, that means FB will be in a straight line to BG. And now we complete the parallelogram AC, the complete one. So we have to complete this rectangle and we have to complete this rectangle. So let's do that. What the lemma is saying is that AC is also going to be a square and DG is a mean proportional between AB and BC. So you might think, how can there be a mean proportion with respect to figures? But think of it like this. BG is this rectangle. So we are talking of the area of this rectangle, which will be some magnitude. Similarly, AB will have an area. BC will have some ratio, area. So which means the area of BG is a mean proportional between area of AB and area of BC. And the lemma is also saying that DC is a mean proportional between AC and BC. So let's take it one by one. DB is equal to BF because this is a square. And BE is equal to BG again because this is a square. Means DB plus BE is equal to BF plus BG. So which basically implies that DE is equal to FG. DE is equal to AH and DE is equal to KC, which means AH is equal to KC. Similarly, FG and AK and FG and HC are equal. That means AK and HC are equal. That means the parallelogram AC is equiangular and also rectangular. That means AC is a square. So we have taken care of the first statement. FB is to BG is equal to DB is to BE. The sides about the equal angles are proportional. FB is to BG is equal to AB is to BG. Figures between the same parallel lines are proportional to the bases. So FB is to BG as the figure on FB is to the figure on BG. Similarly, DB is to BE is equal to the figure on DB, that is BG, is to the figure on BE, that is BC. Let's look at the first statement. FB is to BG equal to DB is to BE. Now FB is to BG is equal to AB is to DG. So let's substitute this. Similarly, DB is to BE is equal to DG is to BC. So that means we can say AB is to DG is equal to DG is to BC. AB is to DG as DG is to BC. Now this proportionality itself tells you that DG is the mean proportional between AB and BC. So we have shown that the second statement is also true. AD is to KD as KG is to GC. Taken jointly, we can say AK is to KD is equal to KC is to CG. AK is to KD, AK is to KD is equal to AC is to DC. Again, AK and KD are the bases and AC and DC are the figures on AK and KD between the same parallel lines. We also have KC is to CG is equal to DC is to CB. Again, KC and CG are the bases and DC and BC are the figures on these bases between the same parallel line. We can write this proportionality AK is to KD is equal to KC is to CG as a proportionality. AC is to DC is equal to DC is to BC. Why? Because AK is to KD is equal to AC is to DC. So we substitute. Similarly, KC is to CG is equal to DC is to CB. So AC is to DC as DC is to BC. So again, looking at this statement, you see that DC is the mean proportional between AC and BC. So that was the lemma. Now let's look at the proposition. It says, if an area is contained by a rational straight line and the first binomial, then the side of the area is the irrational straight line which is called binomial. Okay, it's a bit tricky. So let's proceed and we will understand what this particular statement means. Let the area AC be contained by a rational straight line AB, a first binomial line AD. Divide AD into its terms at E. Remember, AD is a first binomial line and it can be divided into its terms at only one point. So we have to find that point. So E is the point at which AD gets divided into its terms. And AE is greater than ED. So AE and ED are rational straight lines commensurable in square only. This comes from the definition of a first binomial. Since AE is greater than AD, the square on AE is going to be greater than the square on AD by the square on a straight line commensurable with AE. Again, from the definition of the first binomial. And AE is commensurable with rational straight line AB set out. Let's bisect ED at F. So we have to find the midpoint of ED. So F is the midpoint. Apply to AE a parallelogram AG by GE equal to EF square. Or we can say the square on EF. We have to find a point G such that AG times GE, which is nothing but the rectangle on AE, the area of that rectangle is going to be equal to the square on EF. That means AG is commensurable in length with GE. So now draw GH, EK, FL parallel to either AB or CD. So let's draw those lines. Now construct SN is equal to AH. So we have to draw another figure SN whose area is equal to AH. Okay, so the area of this is equal to the area of AH. Construct NQ is equal to the area of GK. Complete the parallelogram SQ. So that means we have to complete this rectangle and this rectangle. As we have seen in the lemma, SQ is a square. AB by GE is equal to EF square. Then which means AG is to EF is equal to EF is to GE. AG is to EF as EF is to GE. AH, which is the figure on AG, is to EL, which is the figure on EF, is equal to the figure on EF is equal to the figure on GE, that is GK. So based on this proportionality, we can write this proportion. It means EL is a mean proportional between AH and GK, and EL is mean proportional between SN and NQ, because SN is equal to AH and NQ is equal to GK. So MR is also a mean proportional between SN and NQ. Why? Based on the lemma. So here EL is equal to MR equal to PO. AH plus GK is equal to SN plus NQ, and EL is equal to MR, and since MR is equal to PO and EL is equal to FC, because F is the midpoint. So we can say this is equal to this and this is equal to this. That means what? AC, the complete rectangle here, is equal to the complete square here, which is equal to MO square. Now, how did this suddenly MO square come? Because remember, this is a square. SQ is a square, which can be written as MO square. Why? Because MO is equal to the one of the sides of the square. So we can say MO square, and which means MO is the side of AC. Or more appropriately, if I have to elaborate it, MO is the side of a square whose area is equal to the area of AC. So this is what the statement means. So that we have shown. Now AG is commensurable with GE. AG is commensurable with GE. Here we have already shown that. AE is commensurable with AG and GE. AE, if it is commensurable with GE, that means the sum is commensurable with a part, then the sum is also commensurable with the other part. AE is commensurable with AB. AE is commensurable with AB. That means AG and GE are commensurable with AB. And AG is rational. So both AG and GE are rational. That means AH, which is the figure on AG, and GK, which is the area on GE, are rational. And AH is commensurable with GK. Why? Because AH is a figure on AG, GK is figure on GE, and AG and GE are commensurate. So AH is commensurable with GK. Now AH plus GK is equal to SN plus NQ. Now SN is the square on MN and NQ is the square on NO. So we can say MN square plus NO square. Now MN square and NO square are rational and commensurable. Why? Because AH and GK are rational and commensurable. AE is incommensurable in length with AD because they are commensurable in square only. AE is commensurable in length with AG. ED is commensurable with EF because F is the midpoint of ED. AE is commensurable in length with AG. ED is commensurable in length with EF. AE and ED are incommensurable in length. So that means AG is incommensurable with EF, which means the figure on AG, that is AH, is incommensurable with the figure on EF, that is EL, which means SN is incommensurable with MR. Why? Because AH is equal to SN and EL is equal to MR. SN is to MR as PN is to NR. These are the bases and these are the figures on those bases between the same parallel lines. That means PN is incommensurable with NR and MN is incommensurable with NO. MN and NO are both rational. MN and NO are commensurable in square only because they are incommensurable in length but commensurable in square. So which means MO is binomial and the side of AC. That was proposition number 54 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.